to design a microstrip patch antenna using CST Microwave Studio. So the microstrip, for designing a microstrip patch antenna, we have to use Microwave Studio in computer simulation technology software tool. This is one of the high frequency software. And over this, when we have to design a new planar antenna, we have to select new project template. So click over the new template, and over the new template, the project template for this particular application is microwaves and RF. So click over there, and over that we are designing an antenna, and so I am selecting antennas, then next button. And over the antennas we are selecting the workflow as planar patch antenna. So I am clicking over planar patch antenna, then again next. And over this patch antenna we have to use time domain solver. So I have selected time domain solver, then again I have to click over the next to define the project template. We are doing this. And next is units. Obviously for microwave antennas we have to use dimension and gigahertz range of frequency. So again next, then settings. Here we have to fix what is the start frequency and stop frequency. I am defining it as 0.5 gigahertz to 4 gigahertz, and I am monitoring the response as E field, H field and far field, and I am defining the frequencies at 0.5 gigahertz, 1 gigahertz, 2.4 gigahertz and 4 gigahertz. So again I am clicking over the next, so that the summary of the project template what we have given is coming over here. So we have selected microwave and RF antenna which is of planar type, and the solver what we are using is time domain solver. In this the units are gigahertz, nanosecond, and the start and stop frequencies are 0.5 gigahertz to 4 gigahertz. The monitors are E field, H field and far field, which are defined at 0.5, 1, 2.4 and 4 gigahertz. Okay, so this is the project template. Just click over the finish, so that one window will pop out where the working model window will come over here, where the 3D window and schematic windows will be coming. In schematic we just pick and place the elements, and in 3D we will have layout windows. And here it is the navigation tree where all the components what we are designing over here will get updated, and in the progress window we will see the simulation status. And we are designing a microwave patch antenna, so microstrip. So for microstrip patch antenna, it has been defined with 3 layers as a capacitor. Over the 3 layers, ground, substrate and patch layers will be there, where the ground and patch layer are made of pure conductors and the substrate layer is with dielectric. So we have to define 3 layers, and first we will design over the ground layer, and for that first we have to check with the home tab, over which units the simulation project check, solver, parametric sweep, everything will appear. And when we go for modeling, import export option with other 3D files, that is other 3D softwares will be there. We can import or export files to those softwares, and that's visible over here. And the background material library is available in the modeling, and moreover shapes are also available. And here we can pick the cuboid shape, which is named here as a brick. In the brick model we have to place over here as the ground in 3D pattern. So I'm just selected the brick, and in the working plane I'm just double clicking. Double click means the outline will come, and again you have to double click and drag so that a 3D object will appear over there. So again double click. Whenever you do this 3 double clicks to define a cube, a window will come, the brick window, brick parameter window. Over that I am giving the dimensions. For this patch antenna I am defining the parameters, that is the dimensions over x, y and z direction. So over the x direction I am giving the dimension as minus 32 to 32. Here also minus 32. In y also minus 32 to 32. And for copper we are using, for ground we are using perfect electric conductors. That is, perfect electric conductor means we are using a conductor perfectly conducting material, and for that in most case we use copper. The commercially available copper is of thickness 0.035, and so there is 35 micrometer. So 0 to 0.035. Here the dimensions are given in mm, and so I am giving the thickness of the copper as 0.035, and the material is PEC, perfect electric conductor, which is having the characteristic similar to that of the copper or gold or aluminium, and so we are just giving it as PEC, perfect electric conductor. And now preview, so that the layer what we have defined with the dimensions will appear over here, and so I'm giving OK, and the name I'm giving it as ground. This is defined as the ground layer. So ground, okay. So ground has been updated in the component list under component 1. So ground is PEC, okay. So in most cases the ground and the dielectric are having same dimensions. So for dielectric I'm again selecting over the brick and clicking over the same dimension, or otherwise we can adjust over the parametric window. And this is substrate. The substrate what we are going to use over here is FR4. There is epoxy glass which is used for PCB material. So it is minus 32 to 32, again Y minus 32 to 32, and Z is, here we have already defined one layer, the second layer we are defining. So the dimensions charts for the substrate height is at 0.035 to the commercially available FR4 layers are of 0.8 mm, 1.6 mm and 3.2 mm. Here we are using 1.6 mm. So 1.6 plus 0.035 mm. So 1.635 mm. And I am grouping it under component 1 itself, and the material is FR4. Here FR4 is not available, and so I have to load it from material library. So the material, I am selecting the material library, and over this FR4, move to search for FR4. So FR4, F4, see here we are having E and then F, S. So the in practical case we will use FR4 is of lossy type, and so just select FR4 lossy. For this the epsilon value is 4.3, mu value is 1. So I'm just clicking over the load, and so it will be loaded over the design. So FR4 lossy is loaded over here, and click over the preview, the same dimension, and so it's set over the ground plane, and then click OK. So we have defined the substrate also. And then next to this is patch layer. Patch layer means signal, that is topmost layer. So for the patch we have to define feed lines. To define feed lines we have to check with the impedance matching. So impedance matching means the most applicable efficient matching is with 50 ohm impedance. So for 50 ohm impedance, to select the 50 ohm impedance, we have to select the feed line width and substrate thickness. Based on that only we are achieving impedance matching. So for that you can use online microstrip impedance calculators. Most of the websites, Radar Tutorial, Pasterneck, like those websites are providing microstrip impedance calculator in online mode itself. Otherwise you can follow with David Kitching, Bell, or some other antenna books. In all books the empirical formulas are available, and if you check over that and work out with those problems, the width of, for 1.6 mm thickness substrate, the width of feed line for a microstrip antenna will be 1.6 mm, 1.56 mm. So 1.56, that is minus 1.156 to 1.56, that is 3.2. So here 3.12, I am defining again a brick over here for feed line. So this is feed, and here x minimum is, it's starting from minus 32. I am defining it as up to minus 16. So feed line based on the impedance, stub matching, single stub matching and double stub matching, we have to go with lambda by 4, lambda by 2 pattern, and so here I am giving minus 16. And for impedance matching, line impedance calculation, based on line impedance calculation formulas, the width of the feed line has been fixed as 3.12. For 3.12, as it is in the median line, we have to give minus 1.6 to 1.6, that is 5.6. I will show up this, how the line impedance has been calculated. So I am going with a pasture neck measurement. So it will open. Till then we will do the design. I will show that minus 1.56 to 56, and the patch is at the top layer over the substrate. The substrate thickness is 1.635, is ended with 1.635. So the feed line thickness has to be started from 1.635 to, again it is copper only, and so the thickness is 0.035 for this feed line, and so 1.635 plus 0.035, which is the thickness of the feed line, copper thickness 0.035. And here we have to change the material also, which is as PEC, perfect electric conductor. Copper is perfect electric conductor. Again do the preview and then click OK. Okay, so now we have to give the patch. So again click the brick and double click, drag, double click, again drag, and so the parametric window will come, and here you have to give it as patch. So we have ended up the feed line with minus 16 mm in x direction, and so minus 16 to 32. 32 is the dimension what we have fixed, and y minimum is from minus 32 to 32. I am covering the full region of the substrate, and so minus 32 to 32. And here again the same dimension, that is z dimension, as that of the feed line, and so 1.635 to 1.67, that is 1.635 plus 0.035 is 1.67. This is also PEC in the same layer, and so again a preview and then OK. So we have defined the top layer also. So this is your patch, feed line, substrate and ground. And now this patch and feed line are on the same planes. So we can add feed with the patch. So I am clicking over the patch. We can use either Boolean operation over here, or otherwise just click the plus button in the keyboard. So patch plus feed. So it has been added like this. See here the partition is not seen. It has been added. And now we have to define port. See, all the cuboids are having 6 faces. Over the 6 face we are having the feed line over minus x direction. So at minus x only we have to give the feed line. So minus x direction means just first you have to and the feed is has to given to the patch line only. That is in the top layer only we are having patch. Over the patch only we have to give the feed line. So just rotate it to get the minus x direction. So like this, and zoom up to accurately get the minus x direction of this feed line. So I am zooming up, and if you select this component 1, it has been clearly viewed. There is here it is ground, substrate and patch, feed of the patch. So I am zooming further, so the layers is clearly visible, and now I have to give the port over this minus x plane. So I have to, if I picked this place, it will be easy for me, and so I am picking the face. So to pick the face, we are having an option in the software as pick face option. Just you have to click F and click over the face where you have to select, and I'm clicking here pick face, and we can toggle the layers also, and I need only minus x direction, and so I'm selecting over here itself. So minus x, and now pressing the space bar, you will zoom out this. So if you want to see where you have selected, you can just zoom in. Okay, so now here in this minus x point you have to define the port. As I have already told you, all the mobile phones are getting signals, right? So it is not for low frequency signals only we will select one particular point and there we will give the source. But for microwave signals, that is high frequency signals, we won't select one particular point and give the source. We will select one phase and give the source. So that only we have selected this phase. So just define the port, go to simulation tab, there waveguide port and discrete port are present. Discrete port has to be given when a particular point has been selected. Waveguide port has to be given for phases. So I am selecting waveguide port. So clicking over the waveguide port itself, the window will pop out because already we have selected the ports. So it will come like this. So now you have to give here. So whenever you are using mobile phone, the mobile phone won't get the signal at one particular point. It has to acquire the signal from a particular region. So we have to extend the port region further. Here I am extending 5 mm further over all directions. So I am clicking 5 mm extra over here, 5 and again 5. So I have extended the region with 5 mm in all directions, and all other are same only, no, nothing to be changed. So I am clicking OK, and so the port has been defined like this. So like this only the port has came. And now we have to check all other background things. That is, first one is frequency. So the frequency already we have given as 0.524, and background is normal, and boundaries, here it has been given as open at space, but in x minimum direction, that is minus x direction, we have given the port, and so give here et equal to 0. As per the boundary condition, at the start point it is et equal to 0. So click et, there is no electric field intensity where the port has been given as per boundary condition relation. So just click et equal to 0 at minus x, that is x minimum, and click OK. So that's it. And now we have defined everything. So we have to go for the solver. So time domain solver we have given at the start itself. So just click over the solver setup. Here we are using hexagonal mesh type and accuracy of minus 40 dB, and the source type is all ports. So just only one port we are using, and so leave it as it is and start time domain solver. So it has been updated in the progress window. Okay, so for every antenna we will categorize the antennas and check the performance based on the S parameter, that is scattering parameters. Here we are having only one port, and so we are having we have to check with S11 over here, and 2D results we will get surface current distribution, H field and E field distributions, and in far field we will get three-dimensional radiation pattern. So this is what present over here. And here see, port, in port we are having the port, and in field monitor whatever the field monitor we have defined at first will appear over here. And see, with the simulation itself the parameters are getting updated. Okay, so after, if steady state criterion is met, see, steady state energy criterion met, solver finished successfully. So the simulation has end up successfully. So now we have to check with the S parameter. So only one port, and so S11 is only present. If two or more ports are present, then that much S parameter values we can get. So S11. So for this we got if the result is less than minus 10, it is the performance is acceptable. So I am selecting just this frequency. So here we are having some free, because of up to the edge we have used, and so it's coming like this. So I am just changing the patch value. So here I am making it as 28, minus 28, and 20, again 28. So everything will change now. So again time domain solver. So again start. So again the simulation will have been started. So we are in need of the accurate results, and so we are doing simulation once again. Okay. So everything will get updated now, and we will check with the result. And see, in simulation window you will get, in addition to time domain solver, all solvers will be present, and in post processing we are having S parameter calculation. Here also import, export, eye diagram, spice extraction, everything will be there. And in view option, you can view, that is, you can zoom, you can pan, you can rotate, you can dynamic zoom and rotate in plane. Options are present. And you can hide components also. Then access scaling, orthographic view, everything is present within the software itself. And here view options are also present. So the simulation has been ended. So for S parameter, see the change in output. Okay, so 2.5 we will see with this itself. So pressing the M key, the marker has been enabled. So just double click over here. So at 2.5 gigahertz we will get minus 18 dB. That means it is acceptable range. So for minus 18 dB we will check with the E field. So E field 2.4 is we have defined it at 2.4. So we will check with 2.4. So 2.4 is not acceptable range, and so I'm moving with I'm defining again with the simulation in the field monitor. I'm giving 2.5. 2.5. Okay, again far field at 2.5. So okay, and again here H field surface current 2.5. I'm making it at 2.5 because the output is received at 2.5, and so I'm making the correction. And again I'm doing time domain solver because it will get updated once we have simulated. So I'm giving again simulation like this. So we have to wait up to the simulation has to be ended, and meanwhile we will see the pasture neck. See, in pasture neck we are having online microstrip calculator. So here we have to give the dielectric value, which is 4.3 as what we have given. Width I'm giving as 3.12. We are using and so here I'm selecting millimeter. Height is 1.6 we have given. Here is millimeter. And see, here the calculated result will come over here whenever we are giving calculate. So I'm just calculating for this width, height and dielectric constant values. So whenever we are clicking over the calculate, for this width and height, the effective dielectric constant is 3.267 and impedance is 50.17. If you increase or decrease the value will get disturbed. Impedance value will get disturbed. And this value has been calculated using the formulas given over here. And this is the width of the field line, this is the height of the dielectric without considering the height of substrate and ground. So and here the definition for microstrip and whatever the associated things with a microstrip patch antenna have been given over here. This is one of the best website to measure the microstrip impedance, line impedance. Okay, and now we will check whether the simulation has been ended. The simulation is ended, and S parameter, so the same result at 2.5, right? So we will check field monitors. E field monitor at 2.5 is 2.5. So shift A, if you give shift A, animation will get started. So this is E field monitoring, and we have to check H field monitoring also. So for H field monitoring, H field shift A, so the animation will start for H field monitoring. And now we have to check with the surface current too. Surface current at 2.5 gigahertz. So the surface current, both E field and H field will combinedly come like this, so that we can find how the electric field distribution and magnetic field distributions are present over here. And the current value has been displayed over here. Okay, and now we have to check with the far field. So far field, the resonance is at 2.5 gigahertz, and so just click far field 2.5. The radiation pattern will appear in three-dimensional radiation pattern will come like this. So just rotate it. It is zoom. So select the rotate pan and rotate it. So it will come like this. It will come like this. Okay, so if you want to see polar graph, you can select polar and you can check what is the radiation patterns. See, as because of the other two bands we are having side lobes, we have to minimize the side lobes, and the magnitude is minus 4.9 dBi here. Okay, like this only you have to see the radiation pattern as well as surface current, H field, E field distributions, as well as S11 graph. So like this only it may come. So this is how a patch antenna has to be designed in CST. Okay. Okay, thank you.